Okay, let us discuss problem number 1.77. Let us first make the diagram. So figure 1.20. So this says there is a horizontal plane. Over this horizontal plane there is a wedge, and then there is a rod that is kept over this wedge. So there is a rod. And this rod is basically constrained. That is, this rod can only move in the vertical direction. It can go up, it can go down. It cannot move laterally. So the rod is vertical. It can move only in the vertical direction. Mass of this is eta m. And mass of this rod is m. Now can you tell me in which direction this wedge will move and why this will move? You see, basically there is a force that will act on the wedge in this direction, normal reaction. So if you see, over this base there will be a normal reaction that will act due to this rod, and this normal reaction will have one x component, nx. This will also have a y component. You're getting? X component of normal action will basically move this base this side, and this rod will move down due to the weight, because this rod also has some weight. So due to weight this will fall freely. All surfaces are smooth, so the mu is 0 everywhere, so no friction. So this means what? If this moves this side, this moves vertically down. Only thing is, in this problem we have to find out the relationship between A1 and A2. So let us say this angle is given to you, alpha. Let us say this is moves with acceleration A1. Are you getting? And this rod is basically moving downward with acceleration A2. How to find relationship between A1 and A2? That is a very important thing in this problem that we have to do. So there are many ways by which we can find relationship between A1 and A2. That is basically called constraint relationship. In this case, I can do something. Let us consider a point here, and this point is just above this plane. So this is a point, a part of this rod. So this is a point just above this plane. So let us consider a point A that is just above the plane, and there is a just point that is just below the plane. That is a part of this wedge. So if you consider, basically these 2 points are the same point, just touching. So that is the touching. So this point is on the plank, that is on the wedge, as well as this point is on the rod also. So this point just below, now I can have a limiting situation in which this point is on this as well as on this. So this point, basically the lower point will have acceleration A1 in this direction. Are you getting? And the upper point will have acceleration A2 in the downward direction. Are you getting or not? Now important point in this problem we have, in perpendicular to this plane, this rod is not pressing this wedge. So this means perpendicular to the plane, this point will have same acceleration that is at this point. This is a very important point, because in the perpendicular direction this point is not pressing to this point. So this must be acceleration component in this direction for this point as well as this point, both should be same. So what I am saying, so if you see, let us take this point. So this angle is alpha. So this point basically that has acceleration A2, and the same thing you can write again, angle alpha, this point has acceleration A1. So what I am saying, in a perpendicular direction, something like this direction, both will have same acceleration. So acceleration in this direction of this point is same as acceleration of this point in this direction, because basically they are not pressing to each other, they are not impinging to each other. So rod is not going inside the wedge. So rod is not going inside the base. So let us call this point 1, this is called point 2. So point 1 and 2, point 1 and point 2 will have same acceleration, perpendicular to the wedge surface, wedge incline, perpendicular to inclined surface. This is the most important thing in this problem, and other things are not so important. We have to only write the equation. Now see, in this direction this angle is alpha, so this angle is again alpha. You can prove yourself. No, this angle is 90 minus alpha. Basically this angle is alpha. So in this direction you will have a1 cos alpha, this side you will have a1 sin alpha. So component of a1 in this direction is a1 sin alpha. Are you getting? Now similarly for a2 you can write, so this is a2, so this angle is 90 minus alpha, so this angle is alpha. So this is a2, so in this direction component of a2 is a2 cos alpha. So what I've said, a1 sin alpha should be equals to a2 cos alpha. Both should be equal. So this means I have tan alpha, even tan alpha is equals to a2. Are you getting? Now things are very easy. I have to write the equation only. Are you getting? And now I have to write one equations. So let us say write down the equations for motion. So let me first make the free body diagram. So this is my rod. There is a normal reaction that is acting on the rod. This is my wedge, and there is a normal reaction that is acting over this wedge. This angle is alpha, so this angle is again alpha, so this angle is 90 minus alpha. So in this direction you will have, so this angle is 90 minus alpha, so n cos 90 minus alpha is n sin alpha. Now if you see this one, I need equation in the vertical direction. So this angle is alpha, this is perpendicular over this surface, this angle is alpha, so this angle is 90 minus alpha. So this side you will have n cos 90 minus alpha, that is sin alpha, and this side you will have n cos alpha. So this side you have n sin alpha, this side you will have n cos alpha. So this component is basically n as cos alpha. You can prove yourself. You see, this angle is alpha. Angle between 9 is equals to angle between perpendicular. So over this line, this is the perpendicular. Over this line, this is the perpendicular. So this angle is alpha. So this side will have n cos alpha. And the weight of rod that is also acting. So eta mg. Eta or simply m. Simply m. So this is mg. No any other forces that is acting. So this is moving this side with acceleration a2. And a2 is basically a1 tan alpha. So let me write a2, that is equals to a1 tan alpha. We have already derived. Now this is coming downward with this acceleration a1. Are you getting? Now I have to write simple equation. So let us write equation and solve them. So for wedge I can write. So if I write equation for wedge, what I will write? I will write n sin alpha force is equals to mass into acceleration. Acceleration is a1 tan alpha. I can write equation for rod in the vertical direction. So rod in the vertical direction, this wedge in the horizontal direction. Rod I am writing in the vertical direction. mg. Okay, wedge has a mass eta m basically. So mass of the wedge is eta m. So I have to write eta m. So mg minus n cos alpha, that is acting up, is equals to mass into acceleration. I can solve for a1. So what we can do is, so let us say equation 1, equation 2. Is this easy? Easily I can solve. So let us multiply this by cos alpha, this by sin alpha, and add 1 multiplied by cos alpha plus 2 multiplied by sin alpha, and then simply add. So you will have cos alpha, and this goes out. So you will have this side mg sin alpha this is equals to eta ma1 tan alpha into cos alpha. So this becomes simply sin alpha. Sin alpha by cos alpha into cos alpha. So I am multiplying this equation by cos alpha. Are you getting? And this equation by sin alpha. So what you will have this side? You will have ma1 sin alpha plus ma1 sin alpha. Aha, we have done one mistake. Can you tell me where we have done the mistake? Here I have done the mistake. So let us say I have to revise this one. What is the acceleration of this block wedge A1? So I have written this is equals to A2. That is wrong basically. So acceleration of this is A1. Are you getting? So this is a mistake. And acceleration of this is A2. And that is equals to A1 tan alpha. So this is A2, that is equals to A1 tan alpha. So many times we do mistakes. So let us modify this. I have to only modify here. So for this, mass is m. So let us write equation for wedge, and acceleration will be simply a1, not a1 tan alpha. So this is simply a1. Equation for 2, so a1 tan alpha. Here I will have tan alpha. Why I am getting this correction? Because when I saw this sin alpha goes out in this equation, I saw that sin alpha goes out. That is important, impossible. And that's why you have to look for some mistakes. So let us rub this one again. So n1, this side will be same mg sin alpha. Are you getting? Now this side you will have m eta ma1 cos alpha. So this is cos alpha plus ma1 tan alpha by into sin alpha. So tan alpha sin alpha. Now this m goes, so this is g. So this g sin alpha is equals to, I can take a1 common, so you will have eta cos alpha plus sin alpha tan alpha. Are you getting? So I can solve for a1. So a1 is basically equals to g sin alpha divided by eta cos alpha plus sin alpha tan alpha. Now I can divide by sin alpha also. So a1 is equals to g divided by cos alpha by sin alpha cot alpha, eta cot alpha plus sin alpha goes out, I will have tan alpha. So this is the acceleration of wedge. A1 is the acceleration of wedge. So I can say acceleration of wedge is, you see how many important these calculations are. If I do some mistakes, then the result will not come out to be. So g acceleration of wedge, this is equals to g divided by eta cot alpha plus tan alpha. Are you getting? Similarly, acceleration of rod, that is a2 is equals to a1 tan alpha you have. So you can say acceleration of rod, that is a2, and a2 is nothing but a1 tan alpha. You see, we have already derived a2 is a1 tan alpha. So you can see your copy, or I can show you. So you see a2 is equals to a1 tan alpha. a2 is acceleration of rod. So rod is a1 tan alpha. So I have to simply multiply this by tan alpha. Tan alpha divided by eta cot alpha plus tan alpha. So this is a pretty easy problem. One important point in this question we have, that the constraint relationship. And how we found the constraint relationship is, we said perpendicular to the incline there is a point that is on the wedge and there is a point that is on the rod. Now this point will have same acceleration perpendicular to the wedge incline. Why this is so? Because perpendicular to the incline of wedge, this rod is not basically pressing to each other. There is no movement perpendicular to the. So this point should have basically relative motion should be 0. That is the same acceleration. So any point that is on the wedge, it should have same acceleration. Relative acceleration 0. If you are just sitting between these 2 points, let us say if you are sitting between rod and base, you will find yourself, if you are sitting on the base, you will find a point on the rod will remain at rest. This means the relative acceleration of a rod with respect to base in the perpendicular direction is 0. This means it has to have same acceleration. You see, in this direction rod will not have same acceleration. So in the direction of incline. So in this direction they have same acceleration. But if you see, consider this direction. In this direction where they will have not same acceleration, because this is slipping in this direction. But in this direction they are not slipping. So I have used in perpendicular direction both should have same acceleration. That is the important point in this question. Are you getting? Okay, let us copy this one and then we'll discuss next problem. I think all of you have copied this one. You just modify the mistake. Okay, let us discuss the next problem.